Hello, organic students. I'd like to talk to you today a little bit about functional groups. Functional groups represent an arrangement of atoms that lend a molecule characteristic chemical and physical properties. The first functional group that I want to call your attention to are the alkenes. Alkenes are just double bonds. We're going to have our next chapter on alkenes, so I don't want to spend a whole lot of time on this, just to point this out to you. And a nice example here is a compound called limonene, which is isolated from lemon peels, lemon rinds, and you can see that we actually have two double bonds in limonene. Alkynes are the name that we give to carbon-carbon triple bonds. We're going to have a chapter just on alkynes as well. And here we have an example. This molecule has an alkyne right here. This is a steroid hormone. Here we have the alkyl halides, and remember that we said that R represents the rest of the molecule, and X generally represents any halogen. This compound, hexachlorocyclohexane, also known as lindane, is an insecticide and a nice example of an alkyl halide. This particular alkyl halide would be considered a secondary alkyl halide, or I guess we could say we have 6 secondary alkyl halides in this molecule. Here we have the alcohols. The general representation for an alcohol is ROH. This example is menthol, and menthol is a secondary alcohol, and it's isolated from peppermint leaves. It gives peppermint its flavor, and it's also used in cough drops because menthol has mild analgesic properties. Ethers can be represented by the general formula ROR. We do have polar bonds in ethers, so the carbon-oxygen bond is polar, with oxygen getting the larger share of that pair of electrons that the carbon and oxygen share. So these are polar molecules capable of dipole-dipole interactions. However, if we compare dimethyl ether with ethanol, an alcohol that has the same molecular formula as dimethyl ether, these two compounds are constitutional isomers. Ethanol is capable of hydrogen bonding, where dimethyl ether is not. And this is reflected in the physical properties of these compounds. So if we look at the boiling points and water solubility, our dimethyl ether has a very low boiling point at -23 degrees C, and ethyl alcohol, or ethanol, boils at 79 degrees centigrade. Dimethyl ether is described as being water soluble in my Handbook of Chemistry and Physics. However, ethanol is described as being infinitely soluble in water in all proportions. So ethanol has a higher boiling point than dimethyl ether and is more soluble in water than dimethyl ether, and this is due to the ability of ethanol to form hydrogen bonds. Here's an example of an ether in a larger molecule. Here's our ether. We also have an alkene in this molecule. We have a hydroxyl group, so we have an alcohol, and we have here an aromatic ring. We're going to do an entire chapter on aromatic rings a little bit later on in the semester. The next few functional groups that I want to describe to you all contain what we call a carbonyl group. A carbonyl is nothing more than a carbon-oxygen double bond. First we have the aldehydes. On one side of the carbonyl we have an R group, or an alkyl group, or we could say the rest of the molecule. But I should point out that for this to be an aldehyde, you have to have a carbon atom attached to one side of the carbonyl and a hydrogen atom attached to the other side of the carbonyl. An aldehyde will always be at the end of a molecule because it cannot be extended at the hydrogen atom. Next we have the ketones. The aldehydes and ketones are very closely related. Their properties are very similar as well. So with a ketone now, we have a carbon atom on either side of the carbonyl group. Next we have the carboxylic acids. On one side of the carbonyl, will have an alkyl group or an R group. It must be directly attached to a carbon. On the other side of the carbonyl, we're going to have a hydroxyl group. This gives us the carboxylic acid. Finally, we have the carboxylic esters. Sometimes you'll just hear these called esters, and that's fine too. The esters have a carbon on one side of the carbonyl, and they have an OR group, or an alkoxy group, on the other side of the carbonyl. All of these molecules have polar bonds. You can see that we have one polar bond for the aldehydes and ketones, but two polar bonds for the carboxylic acids and the carboxylic esters. So the carboxylic acids and esters tend to be more polar than the aldehydes and ketones, and again, this will be reflected in their physical properties. Let's look at some specific examples. Here I have an aldehyde, a ketone, and an alcohol. And they all have 3 carbons, so they're all very similar in their size and their molecular weight. However, if we compare boiling points of these 3 compounds, we can see that the aldehyde and the ketone are pretty close in boiling point. There's only about a 7-degree difference between the two of them. But when we look at our alcohol, you can see that the boiling point goes up significantly, up to 82 degrees for this alcohol, and that's due to the ability of the alcohol to form hydrogen bonds with itself. Let's look at a carboxylic ester and a carboxylic acid. These compounds are similar in size to our aldehyde, ketone, and alcohol above, and our carboxylic ester has a boiling point that's pretty close to that of the aldehyde and the ketone. But look at our carboxylic acid. We have a boiling point of 118 degrees, and that is due to the ability of the carboxylic acid to form very strong networks of hydrogen bonds with each other. This ketone in the middle is acetone. You've probably used that to take your nail polish off. This ester here is called methyl acetate. You've probably also used a very similar ester, ethyl acetate, to take your nail polish off. This carboxylic acid is called acetic acid, and vinegar is a 5% acetic acid solution in water. This alcohol is isopropanol, and you might know it better as rubbing alcohol. Here I have 3 compounds. I have a ketone, an alcohol, and a carboxylic acid. All of these compounds have 4 carbons, and they're pretty close in their size and their molecular weight. But let's think about their physical properties. Our ketone is described as soluble in water, according to my handbook of chemistry and physics, with a boiling point of 80 degrees. Our alcohol is described as being very soluble in water, but it's not infinitely soluble in water. It has a solubility limit. It has a boiling point of 117 degrees. Our carboxylic acid is infinitely soluble in water in all proportions, with a boiling point of 163. And this really represents the general trend that you'll see in terms of physical properties of these different types of functional groups. With ketones and aldehydes, alcohols, and carboxylic acids of similar size, you're going to see this trend. The alcohols have higher boiling points than the aldehydes and ketones, and the carboxylic acids will have even higher boiling points than the alcohols. Let's see if you can identify the functional groups that we've just discussed. Here we have our aldehyde in the molecule cinnamaldehyde. This molecule also has an alkene and an aromatic ring. As I said, we'll do an entire chapter on aromatic rings later in the semester, so don't worry about that too much right now. I have this compound cinnamaldehyde in my lab. It smells really good, and that's typical of the properties of aldehydes. Here I have a ketone, and remember that a ketone has a carbon on either side of the carbonyl group, here and here. This also has 2 alkenes. Here's our carboxylic acid in the molecule ibuprofen. Ibuprofen also has an aromatic ring. Here's our ester group in methyl salicylate. The ester group has a carbon on one side of the carbonyl and an OR, or an alkoxy group, on the other side of the carbonyl. Methyl salicylate also has a hydroxyl group So this is an alcohol and an aromatic ring. Mescaline has an amine. It also has 3 ether groups. ROR is the general formula for ether, and an aromatic ring. Here is a very complex molecule. This compound is called paclitaxel or Taxol. You may have heard of the application of Taxol for the treatment of ovarian cancer. It actually comes from a tree called the Pacific yew, and that tree is endangered. When Taxol was first being developed as a drug, there was a great deal of interest in the synthesis of this compound, Taxol. Kind of interesting, the first chemist to synthesize it was Dr. Holton at Florida State University, and after he announced that he had completed the synthesis, his lab was broken into and someone was trying to steal his Taxol. Kind of a sad story there. But I want you to put the video on pause and take a few minutes and see how many functional groups you can identify. So go ahead and pause and I'll wait. Well, let's see how you did. This is a functional group we haven't talked about yet. It's called an amide. We might get to that later in the semester, so I don't want you to worry about that too much right now. Here we have an alcohol, and this would be a secondary alcohol. Here we have an ester. Here we have a ketone. Here we have an ether. Here we have an alcohol, and this would be a tertiary alcohol. Here we have an alkene. Here we have another carboxylic ester. Here's a secondary alcohol. And here are 2 more esters. And that does it for our functional groups. So how did you do?